In this video, we're going to look at Faraday and Lenz's laws. This is all about understanding how changing magnetic fields, or really changing magnetic flux, can affect charged particles. Right? We've already talked about how moving charge generates magnetic fields, and then moving charges feel forces from magnetic fields. And so what we're going to look at is the kind of opposite of that. If you do something with the magnetic field, can you get current to start flowing? And so that's kind of our interesting idea. Now, we already know this, right? The idea that if you put a current through a wire, you can get a compass needle to deflect, right? You can apply a force to a magnet with a current carrying wire. So can a magnetic field cause a current? And this is our last piece, right? Or our last two pieces. There's this piece here, and then there's inductors, which uses this concept in circuits. So that's what we're going to look at. This is the basic idea behind what we call electromagnetic induction. A changing magnetic field creates an EMF or a voltage, and EMFs, of course, can cause currents if they're attached to a continuous conducting path. And the most important application of the magnetic field for us, because this is the one that allows us to talk about generating electrical power, running motors, so doing useful work using electricity. So we're going to start with what we already know. We know that if a charged particle is moving through a magnetic field, it experiences a force. So just pretend this is a positively charged particle moving along, because there are positively charged particles in that piece of metal. Moving along, the field is in, it should feel an upward force, and the negative charge would feel a downward force, right? So the positive charge and the negative charge would be separated. Some would be pushed up, the positive charge, which doesn't really move, and the negative charge would be pushed down, which it would move the electrons. And so we would get a positive side and a negative side according to this force, right? And if we have a positive and a negative side, what we have is we have a charge separation, we have a potential difference, we have a voltage. And once you have a voltage, you can, of course, attach it to a circuit and cause current to flow. This is actually known as the motional EMF, an EMF generated by moving a piece of metal through a magnetic field. We'll come back and talk a little bit more about that after we do what we're going to do in this video. But to get a current, you need a path for the current to flow through. So what you usually do is you set up this kind of U-shaped channel of a conductor, so that as the conductor that's moving has this potential difference, this EMF, that the current can run around through it. And the current runs around as it would in any circuit, and it looks like that, from high to low potential. So this leads us to Faraday's Law. Faraday's Law tells us all the different ways that a magnetic field can create an EMF and how to get a number for that. But first we have to define something we call the magnetic flux. And we've already talked about flux in general, and then we talked in more specifics about the electric flux. And so what we're going to do now is talk about the magnetic flux. And so magnetic flux, just like electric flux, is how much B field or how much field is going through a surface area. We calculate it this way. Magnetic flux is the integral of B dot dA, or BA cosine theta, where theta is the angle between the area vector, which is always normal to the surface, and the magnetic field direction. Now, of course, there's arbitrary configurations of this, but of course, as always, we're going to pick surfaces that are relatively simple so that we can better understand what's going on. Now, again, flux is a surface integral, not a line integral. It's like Gauss's law, this part of it. And so how do we think about this? Well, if you have a magnetic field going straight up and you've got a surface that is sort of flat on the ground, then the area vector and the magnetic field vectors are in the same direction, so that theta would be 0 and cosine of 0 is 1. You would get a nice big, magnetic flux. And the A is always normal or perpendicular to the surface. So here, theta is 0. Here, theta is 60. At 0, you're getting maximum flux. At some other angle, until you get to 90, where you get 0 magnetic flux, it gets smaller and smaller. So how do we actually do this calculation? Well, generally speaking, the area is something of the things we're going to pick is not a complicated area. The magnetic field is going to be constant everywhere on it. So the magnetic flux here is just the area of this circle, 2 pi r, right, times the magnetic field, pi r squared, times the magnetic field strength. So 2 Tesla of magnetic field times pi r squared times cosine of 0 gives us about 0.063 Weber. Right, so capital W lowercase b is the unit. This is a Weber. It is the unit for magnetic flux. New unit, very exciting. And it is a Tesla times a meter squared. That's where it comes from. More examples of this. Well, if you had a square, as your loop, the surface that you're worried about, magnetic field of 5 microtesla and side length of this square of 2 meters, we could find that the flux is 5 microtesla times 2 meters, quantity squared, times the cosine of theta, 20 microweber. And then, of course, we could do something like this, where we have a magnetic field going up the page and the circle is in the page. The magnetic flux is 0 because the angle there is going to be 90 degrees, and cosine of 90 degrees gives us 0. All right, so what happens then if the flux changes? This is the key to Faraday's law, the idea that if you change the flux, that's how you can induce a magnetic, through a change in the magnetic field, the magnetic flux, a current to flow. So Faraday's law is listed like this. EMF is equal to negative d magnetic flux dt. So in other words, if the magnetic flux changes, you get an EMF. A changing magnetic flux creates an EMF. If the flux is constant, right, you have a magnetic field and you have a ring just sitting in it, nothing will happen. Only if that magnetic flux is changing will you get an EMF. We can check the units. Weber per second, does that equal a volt? All right, that's a good question. You can check it out. But there are 3 ways to change the flux. You can change the magnitude of the magnetic field. And you can do that by maybe bringing a magnet closer or farther away. If it's an electromagnetic that's creating the electromagnet, you can turn up and down the voltage on that. You can change the area that's in the magnetic field, or you can change the angle between the magnetic field and the area vector. Those are your 3 methods. So Faraday's law, let's think about this. So here we have a magnetic field, a radius, and we have a resistance of the coil. Right? If I give you this graph of the magnetic field strength over time, we have constant for a while, then over the time from 2 to 3 milliseconds, it drops from 0.2 Tesla down to 0. We can figure out how much EMF would be induced. And then if we know that the conducting loop has a particular resistance, we should be able to calculate the current. So we have constant flux, changing flux, constant flux. And we expect an EMF to exist from 2 to 3 milliseconds. So let's work on this. Let's do Faraday's law. So from 2 to 3 milliseconds, we're changing the magnetic field. The area stays constant. So the area is pi r squared. The changing magnetic field is negative 0.2 Tesla divided by 0.001 seconds, as you see there. So there's our area of our loop. All of those pieces, pretty straightforward. We get 6.3 volts. Then we use Ohm's law and divide 6.3 volts by 0.5 ohms, and we get 12.6 amps. And so what does that look like on our graph? Well, we have 0 changing flux. It's constant flux for the first 2 seconds, so no current. Then for a millisecond, we have 12.6 amps of current, and then we have 0 again. If the magnetic field reverses direction, does the current reverse direction? Let's take a look. No. And again, it's the rate of change. So this is a negative change all the way along, right? This is kind of like saying that changing your position going from on the positive side of the origin to the negative side of the origin, does that mean the sign of your velocity changes? No, as long as the slope is the same. So the slope of this line of this magnetic field as a function of time is the flux, is the rate of change of flux. So we get for the entirety from 2 to 4 milliseconds, we have a constant current. So what are the ways you could produce a larger EMF? Well, you could add more loops, right? If you had a bunch of loops, then each loop would experience this same EMF. And so we add an N for the number of loops. The more loops you have, the bigger the effect of the EMF. So let's do an example. A 2 meter long wire with a resistance of 1/4 of an ohm is formed into squares. Into a square lies in this B field. The field increases steadily. Find the current. Well, if it's 2 meter long wire, then it's 1/2 a meter along each side. So that's how we get our area. The flux, we are told, starts with 0 magnetic field and goes up to some value. So we have 0 initial flux. So we're just looking at the final flux. It would be equal to the change. So we get 0.1 Tesla meter squared. The EMF then, the absolute value of it, should be the rate of change of that flux. That's 0.1 Weber divided by 0.3 seconds. And we get basically 1/3 of a volt. Then we apply what we know from Ohm's law with the current to find the current of 1.3 amps. Another example, the same example, excuse me. This is now the other piece, but which way does the current flow, clockwise or counterclockwise around this loop? And this is something that may not be immediately obvious. So that is the negative sign in this equation. The negative sign, and correspondingly Lenz's law, which explains why that negative sign should be there, is what we need to investigate now. So Lenz's law tells us the direction of the induced current. And this is a good warning, right? The words to describe it are a little bit convoluted and sometimes hard to understand, but the reality of it is pretty straightforward. So here it goes. The induced current must flow in a direction such that the magnetic flux it creates will oppose the change in the external magnetic flux. What? Basically, it means that if the magnetic flux is increasing, right, say up or to the right or whatever direction it is, you're getting more and more magnetic flux in a particular way, that the current will flow to create a magnetic field in the opposite direction of that. That is what will happen. That's why it's a negative sign. So, for example, if you were to be dragging this bar, moving it to the right at some velocity, the area is increasing. So the internal flux kind of going into the screen is getting stronger and stronger, which means whatever current is induced should make magnetic field come out at you. And that is what we want to do there. And the only way for magnetic flux to come out at you, if you think about the way the first right-hand rule works, is that we need the current to be flowing counterclockwise around that loop so that we will get some magnetic flux from the center of that loop coming out at us. Why does this happen? Well, this is conservation of energy, right? You can't have things change, that just for no reason, right? If the current flowed the other way, as it got more flux and the current flowed that way as a result, then it would have more flux and it would just keep getting bigger and bigger and bigger. It would be infinite energy for no work, which doesn't make any sense. Okay. And the analogy is with inertia, right? There is always this opposition to a change, right? Just like in motion, the more mass you have, right, the harder it is to change the velocity. But in this case, we're dealing with, an attempt to keep the magnetic flux from changing. All right, 3 examples. Magnetic field is increasing in this case. You should, as you're watching this video, maybe pause it, write it down. If the magnetic field is increasing, this is going into the screen. And we're only interested in what's happening inside of the loop. So if the magnetic field is increasing that way, there should be a flux, or that is increasing flux in. That means we should have a current flowing in such a way to make a magnetic field point outward. So that would be counterclockwise. If the magnetic flux or the B field is decreasing, we want to replace some of what was lost. So it should go clockwise. And finally, if we have a magnetic field coming out at us that's decreasing, we want to replace that that's lost. And so that should also be counterclockwise. All right. Magnetic field changes. What is the current direction? Well, we have a magnetic field that is positive to start and it's going down, right? So if this is our picture, we have a magnetic field with the field lines going into the page and it's getting weaker and weaker, which means we should replace it. And then at the second phase, we've got magnetic fields pointing out, but it's getting bigger and bigger. So we want some that will go the opposite that. And so in both cases, we want a clockwise current, because a clockwise current would give us magnetic field in to the inside of the loop. And that's exactly what we need in both cases to counteract the change. There you go. Magnetic flux. Once we understand that it's the field kind of through an area, when that changes, you can induce a current. That current will always flow to oppose the change, right? If you're getting more flux in one direction or more field in one direction, the current will flow to make field in the opposite direction. And that's how it works.